if you have a particular particle, let's just imagine it in the one particle state space. There's no need to add extra particles. It's basically the same argument. Okay. Suppose at some point in time, you know the momentum. Momentum is usually labeled with P. Let's just do it in one dimension as well, just restrict it down. You know the momentum, P sub x, and you know the position, x, at some time, t. We might as well call it t equals 0, so you know this. Now, the force law at the most can only be a function of these things. The force is going to be a function of your state. So if we assume that the state only consists of these two things, which in general it typically does, then what we get is this a function of x and p sub x, and it's going to be equal to mass times d bx dt. Which, if we assume for ordinary particles that the mass is a constant, this is also equal to dpx dt. Now, with this particular setup, we notice that at a certain point in time, the initial point in time, we know where it is and we know where it's going. This is a law of update. This will tell you if you move an infinitesimal point forward in time, if you move forward in time by an amount dt, then p sub x at 0 plus dt, in other words, p sub x at dt, is equal to p sub x at 0 plus dpx dt times, I suppose we should call this delta t, where delta t is a variable which is very, very small. If you use two less than symbols, it's a symbol for much, much less. So delta t is much, much less than 1. Very, very small quantity. So, for values of p of x close to 0, this law of updating works. So all you have to do is plug this in. F sub x at x p of x. And it's x of 0 p sub x of 0 times delta t. I should move this over. It's p sub x of delta t is equal to p sub x of 0 plus f sub x of x of 0 p sub x of 0 times delta t. This law applies for sufficiently small time intervals delta t. The smaller the time interval, the more accurate this is. So, imagine that it's an extremely small time interval. Imagine it's an extremely small time interval. For now. Now, we can also notice that x as a function of delta t is simply equal to initial velocity v sub x of 0 plus d v sub x dt evaluated at 0 times delta t. However, notice v sub x is just equal to p over m, p sub x over m. So, what this is really equal to, what this is also equal to, is v sub x, or 1 over m times the quantity p sub x at 0 plus d p sub x dt evaluated at 0 times delta t. For sufficiently small delta t, that is an accurate formula. So what you do is you cut things up into really, really, really small intervals. Cut things up into really, really small intervals. This is in general not how you solve a differential equation. It's not a very efficient method, but in this case it can prove a point. Cut this into sufficiently small intervals of time delta t. Then, if they're sufficiently small intervals, what you'll notice is p sub x of 2 delta t is equal to p sub x at delta t plus f sub x of x at delta t p sub x at delta t times delta t. And x of 2 delta t is equal to 1 over m times p sub x at delta t plus d px dt evaluated at delta t times delta t. And in other words, you can just keep up that particular formula. If the original delta t was sufficiently small, then this evaluated at 2 delta t will be also fairly accurate. This evaluated, oh, by the way, this isn't at 2 delta t. This is at epsilon delta t. That's more appropriate. Epsilon delta t, where epsilon is some quantity in between 1 and 2. So this quantity over here, it's not really delta t you're multiplying by. It's 2 minus epsilon. Or no, it's epsilon minus 1 times delta t and epsilon minus 1 times delta t. That's what you're multiplying by. That's just the variable there. And once you get this, take this out to 2 delta t, then you can use 2 delta t inside as the arguments of these functions, and that will give you a variable for p sub x up to 3 delta t. And the smaller these intervals are, the more sufficiently accurate you will be able to make these evaluations. The point is that, in principle, in the limit that delta t is infinitely small, it's an infinitely, infinitely small unit of time, that method, in principle, constructs a deterministic time evolution for the system. Now, we also need to know that it's reversible. To reverse it, all you do is take the conditions at some point in time, some later point in time, say you let it evolve until t equals 15 minutes. Okay, now you take the state at t equals 15 minutes, and then let the force go over to minus the force. Let the force that evolves it forward in time go over to minus the force that's going to evolve it backwards in time. And take the initial conditions, take the momentum, and let it go over to minus the momentum. Leave the position the same. Leave the position stays the same. The momentum goes over to minus the momentum, and the force goes over to minus the force, and evolve that system in time 15 minutes, and you will find that you get, once you reset